Explain.
Yes, sir. I have posted in the chat box, sir.
Yeah, tell me. I have the, in the chat box itself. Okay.
Sir, I have posted the question in the chat box, sir.
I don't see it right now.
Yes, sir.
Is it chat box or you put it in the Excel forum, in the forum?
The chat box, sir.
Today's-
in the chat box, sir. In this, sir. In this Zoom meeting chat box, sir.
Meeting chat box. Yeah, where is it? I'm not able to see anything. Balaji, are you able to see? I don't have any
In the
question.
down chat is there, sir. Okay, sir. I am posting again, sir.
Why don't you read it? Yeah, why don't you tell me what the question is? Yeah. Yeah.
Sir, in the case of that particle on a ring,
Yeah.
we are integrated from our 0 to 2 pi, sir. But in that case, the value of phi can be anything, sir. Because under the square integrable condition, actually we are integrating from 0 to 2 pi. But that integration can also be from x to x plus 2 pi. So under
it does not matter. What is happening is, well, you are right.
Yes.
Basically, it can be 2n pi, where n can be anything. But please remember the variables, the particle in a ring, when we talk about 0 to 2 pi, we talk about unique values. The wave function, if you look at, is something like exponential I phi, right?
yes,
Square 1 by square root of 2 pi exponential I phi. That's a wave function that you get, isn't it?
yes,
See,
sir.
yeah.
I am phi, sir.
Yeah, e to the I 2 phi, e to the I phi. That's what it is. Just let me share my screen. Okay, just one moment. Yeah, can you see it now? My screen?
Yes, sir. Yes.
You are able to see. Okay, so let me share the screen and I will tell you what it is in journal. Okay. So when you talk about a particle on a ring, okay, something like this, it is 0. This is the angle 0, and then the position is at any interval d theta or d phi. Okay. D phi.
Yes, sir.
And the wave function psi of phi is the same as psi of phi plus 2n pi, where n is an integer.
Yes.
Okay. Therefore, the unique wave function is defined only for psi phi with phi between 0 and 2 pi. Sorry, one moment. Let me post the wave function is defined uniquely with phi between 0 and 2 pi. So this is periodic function. Please remember, it's a periodic function. Therefore, we do not worry about phi plus 2n pi. You can also say, I mean, essentially the interval should be 2 pi. Okay. So you can start from minus pi to plus pi. You can start from pi to 3 pi. It does not matter. Okay. What matters is every point on the circle represents one unique value of phi, and everything else is generated by how many times you go around the circle. Isn't it?
Yes.
Therefore, it
Yes.
does not matter. Therefore, the wave function is defined only. This is also there in the psi of phi being 1 by root 2 pi e to the I phi. You know where n will come. Where n will come. N will come with respect to the energy, the quantum number n square will be there for the energy, and that's because you have the the rotational kinetic energy is minus h bar square by 2 pi d square phi by d square psi by d phi square is equal to m square, isn't it? Psi or n square psi.
Yes.
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 Okay. This is
Yes.
where the energy will have the quantum number n. And if it is energy is n, you will write to the wave function psi of phi as 1 by root 2 pi e to the 2 I n phi.
Yes.
Okay. So that's the only place, but the wave function is defined for only between phi is equal to 0 and phi is equal to 2 pi. Uniquely. So your question that this n is there will also be taken into account. Okay. I don't think you should have that, but yeah, it's basically this is a boundary and it's periodic. And we don't talk about the motion of the particle. We talk about the probability of finding the particle on a certain region of the circle. And you will see that the probability is simply proportional to d theta divided by 2 pi.
Yes.
If the d theta is large, it's linear. The proportionality is such that the probability for equal intervals is always the same. If d theta is the same, d phi is the same in one region or another region, the probability of finding the particle is always that d phi divided by 2 pi, because this goes to 1 when you take psi star psi, this function.
Yes.
Yeah. Okay. That's it. Yeah. That's the answer to the question. Okay.
Yes.
Any other? Yeah. Any other question?
Yes. One more question was there, sir.
Yeah. Go ahead.
In quantum theory, sir, actually we have all the orbitals. All the orbitals actually range from r equal to 0 to infinity. All the orbitals range from r equal to 0 to infinity, no, sir?
All the orbitals are from 0 to infinity. Yes, radial and angular. See, the radial will be 0 to infinity. The angular will be 0 to pi for theta, and phi will be 0 to 2 pi. Yes.
Yes, sir.
Yeah, that's correct.
So, sir, if we are exciting any atom, so if any electron is getting excited, then the overall the probability distribution function is changing. Yeah, that's right. If any excited atom loses a photon and its energy comes down, then in that case, again the reorganization of electron density takes place. Yes. Yeah. So, sir, whether this reorganization of electron density is instantaneous or it takes some time, sir. Okay, you cannot talk about that. Whether this time is yes. Yeah. In quantum mechanics, in the transitions that we are looking at as a property of change in energy. See, if you have to look at the lifetime of the electron in a certain given state, okay? Yes. Then you have to worry about solving the time-dependent Schrodinger equation. Okay? The orbitals are stationary eigenfunctions. Okay, they are not time-dependent, and therefore, as far as the way we do it, the transitions are instantaneous. Okay. Yes. They happen with 0 time change in between. But what you are doing is measuring the probability of finding the electrons in the excited state or in the ground state. Yes. That's all you are measuring. Okay, yes. That's all you are able to calculate. You cannot calculate the transition time it takes because time has not formally been introduced in our H psi is equal to E psi equation. Yes. Okay. Yes, sir. There is no time. Yes, sir. Then what is the source of that line width, sir? In the previous slides, you were telling that's different. Yeah. The line width is a different issue altogether. The line width simply says basically that the molecular upper energy state
if it is an excited state, it has a finite lifetime. Okay.
Yes.
Molecule, if it stays in the upper energy state for infinitely long time, that is also a stationary state. Okay, that's also a stable state. It's not. The excited state has a finite lifetime, which means the excited state is not a very precise value. Okay? The excited state is not E, it is E plus delta E. Okay? So the excited state is spread over a small energy distribution, delta E. Now, the lifetime of the particle that stays in that delta E is given by this Heisenberg's uncertainty relation. Delta E delta T is greater than or equal to h by 2 pi. Okay, so the line width is due to the fact that either the same species you are measuring many times, or you have a large number of the molecules. Simultaneously, you are measuring the absorption of various molecules and plotting it. Some molecules will be in a slightly different energy level because of the delta E. They may be slightly above or below. And therefore, what you are seeing is not the transition at E, but the transition taking place between E and the delta E. The delta E is in the is in the axis. So the natural line width essentially tells you that no excited state can have an infinite lifetime if there is a transition. The excited state dies down with the lifetime of with the electron in that excited state lifetime being delta T. So the line width comes from the basic requirement for spectroscopy that the E naught, and then you have an E which is a delta E. Okay, delta E. This delta E and the lifetime that the particle stays in this excited state before it undergoes transition, that delta T is greater than or equal to h by 2. This is the natural line width that we talk about. H bar by 2, sorry. H bar by 2.
Sir, you have shared the screen, sir.
Yeah?
Screen share panela.
Say it again? Sorry, I didn't get it.
Screen share panela.
Yeah, it is not a sharp transition. That's right. Yeah. Go ahead. Any other? Does it make sense?
Yes, sir. Yes.
Okay. So any other input from any of you? One.
Sir, your screen is not shared, sir.
No. Just now I shared the screen, and now I have connected. Oh, wait a minute. I thought I shared the screen, but then I probably switched it off. Okay, here it is. Now, can you see that? No.
Yes. Yes, sir. Yes.
Yeah, you can see that. Okay, great. So the excited state is usually a spread in energy. This is what happens. If the excited state has a very short lifetime, okay, it's very fast, it decays extremely fast. You see that the spread of that energy in that excited state is very large. That is that a state cannot be very precisely defined. Okay, that state has to be defined just one moment, otherwise we will lose connection. Because then I will lose connection. Okay. So the excited state has to have a spread in its energy distribute, the energy of the state. What it means is that if you have many molecules, some molecules may be within this spread delta E, some may be here, some may be here, here. But when you measure the probability of transitions, you will see that those which are here will have a transition. Suppose this is precisely E, okay? Those which are here will have a transition somewhere. Here, some will be here, some will be here, some will be. So you can see that the energy sort of spreads out. This is the minimum spread, by the way, okay? Molecules have line widths due to other factors. What happens is molecules are moving. Therefore, when the molecule is, moving, the energy it emits while it's in motion is not the same thing as the energy it will emit if it is static. Okay, this is known as the shift what is called the Doppler shift. Okay. Therefore, the Doppler shift can also contribute. The Doppler shift happens when there are lots of molecules, when there are fewer molecules, and therefore what happens is the molecules are emitting at different energies. Now, if you increase the pressure of the system, what happens is the molecules undergo a lot of collisions. Therefore, their speeds are constantly changing. Therefore, the energy that they emit for a particular transition, even though it is the same transition from one energy, E1 to E2 for all of them, the energy that is emitted will be slightly shifted on either side. So that is also called the pressure broadening of line width. And then there are other effects. The line width of an excitation is dependent on the surroundings. The intensity of the spectral line width is dependent on the population distribution. How many are in certain energies, how many are in certain energies, and so on. Whereas the frequency is usually independent of all of this. Frequency is a fixed quantity. So you have to worry about all these things when you study a spectrum. Okay?
Okay, sir.
Yeah. Okay, so I see one more student was joined, or maybe more. Let me see. Yeah, there's only one. Oh, that person left. Okay, so Sandeep, do you have any other questions? Are you happy with what you are able to read?
Yes, sir. Well,
is it useful?
Yes, sir. Yes, sir. It is good course, sir.
Okay.
It is a good course.
You are happy with it? If you have,
it is useful, sir. Very much useful, sir. Because
okay, great. I think it clears some of the things that you read in the books, isn't it? And you must listen to the lectures.
Yes,
how the algebra is done. I do not hide the algebra. I usually put the algebraic steps very, in detail. Therefore, you should be able to follow that. Okay.
Yes.
Yeah.
Sir, I was reading Atkins, sir. Atkins. In Atkins, they are using the term orbital approximation, sir. So they are saying under the case of orbital approximation, they can take the wave function psi as the product of two individual orbital wave functions. So in that case, they are neglecting the contribution of electron repulsion, sir. But in case of, sir, in your lecture, sir, you used H2 plus molecular orbital. And in that case, under the valence bound condition, you also use that the product of two wave function.
Yeah.
So, but there, in that case, we have used the contribution of electron repulsion.
No, if it is a H2 plus, there is only one electron.
Yes, sir.
Therefore, there is no electron.
Yes, sir. But from after making
the repulsion energy.
After making
for hydrogen,
H2,
you have. For
yes,
H2
sir.
molecule, you have. No.
Yes.
What you do is Hartree-Fock approximation includes partially the electron correlation. What happens is, what is the Hartree-Fock approximation? It looks for the one electron wave function, right? So
Yes.
a single electron now in a sea of there is another electron. Okay. Therefore, the potential energy of this electron is not only the potential energy of this electron with the nucleus, but it's also with the other nucleus. But there is a small contribution, that 1/r distance between them. When you use the potential energy for the one electron, you are taking into account the effective potential at that point for the electron. The effective potential is contributed by nucleus 1, nucleus 2, and also electron 2. Okay. Electron 2 contributes a little bit, but you are looking at the potential of the electron 1 as a function of its coordinate. You are not looking at the electron 1 potential as a function of the electron 2 coordinate. You don't do that. Okay. If you include the electron 2 coordinates and electron 1 coordinates, the 1/r12 becomes an exact term. That is what you do when you solve the electron correlation, when two electrons are interacting with each other and they repel each other. You don't do that. Hartree-Fock corrects very, very small amount of the electron correlation by taking the effective electron potential due to second electron at the electron 1 as a function of electron 1 coordinate, R1. The potential is dependent on R1 minus R2, please remember. Okay. If this is R1 and this is R2, the potential depends on the distance between them. But you are considering this as an effective, and you solve the one electron equation and you get a better wave function, and use this wave function to again calculate the effective potential, because you are using the same wave function for the second electron also. When you say one electron wave function, these are two individual one electrons. Therefore, you are using the one electron wave function here to that, and then the probability, the electron distribution, the energy gets corrected. Therefore, electron correlation is not completely accounted for in the Hartree-Fock approximation. A small amount. That self-consistency means that when you do this repeatedly, you will reach a particular point. And once you reach the point, you can't change any further. That point is called the Hartree-Fock energy. But it's not the exact energy. No. Okay. To solve the problem, you have to solve the two electron correlation problem more exactly. And there are other methods, and the density function theory does that. And also then other functionals are there, which are correcting approximately. The exact solution is not possible, by the way. Okay. Exact analytic solution cannot be found, but very close, very good numerical approximate solutions can be found using computers, using numerical methods. Okay.
Okay, sir.
Yeah. Okay. Any other? So you are really moving forward. You are moving further towards the Born-Oppenheimer, towards the these things. Okay. Good. What are you doing? You are doing your final year. You are doing your MSc, or you are studying for the GATE, or what? What you said something last time. I forgot.
Yes, sir. Actually, I gave a NET exam this time, sir. NET exam.
You are writing for the NET exam. That's right. Oh, okay.
Yes, sir. NET exam.
Okay.
Actually,
Okay.
I
Yeah.
passed out in 2009, sir. 2009, long back from
Okay.
IT Kharagpur. So
Okay. Now you are recollecting all
long
this.
back, but
Yeah.
yes, yes.
Okay, good. If there are no other questions, then I will ask basically Balaji. Balaji, do you see anybody else? This is not YouTube, right? This is not on the YouTube. This is a direct link. Balaji, are you there? Are you there, Balaji? Who is there at IIT Madras now? That link. Okay. So Sandeep Kumar, if there is no other question, can I leave then? I thought the others will join.
Hello.
Yeah, Balaji, there is nobody else waiting in the YouTube or anything, right?
Yes, sir. We are also streaming this on YouTube. We can close it.
No, but there is no one. There are no questions from YouTube, right? There's
No, sir,
one.
no, sir.
So therefore, we can close this. Okay. Since Sandeep Kumar has clarified whatever he needs to, I want to thank him for joining, and then let me close. Okay. All the best
Yes,
to you,
sir.
Sandeep. All the best to you, Sandeep. Okay.
Okay, thank you, sir.
Thank you. Okay. Balaji, we can close this because I don't see any.
Yes, sir. Yes, sir.
Madhu, they are there. Anyway, while they are there, where is assignment? Where is tutorial 6? Madhu.
Sir, I have one doubt, sir, that
Go ahead.
in this assignment 5, sir. In assignment 5, the question number 3 is, sir, again the answers are not matching. It has asked for the degeneracy of 6G orbital, but the options given are not matching, sir. That,
Degeneracy of which one?
Question I can paste, sir. Question.
No.
G, sir. 6G orbital.
6G
orbital.
G orbital.
Yes.
6G.
And also, yes, sir. Also, it has asked for the number of radial nodes, the number of angular nodes, and this
Okay.
degeneracy, sir.
Do you get?
Fact, it has asked.
Is the degeneracy?
Yes.
Is the degeneracy 36? Does it say 36? Is that the answer?
Yes, sir. Yes, sir.
36 is there.
36 is the answer is there, sir. 36 is
36 is the correct answer because the degeneracy of the orbital is basically the n square for
there. Yes,
any.
sir. 36 is there.
Yeah, but then if you look at the angular and the radial nodes, you see the radial. Let me share the screen. Okay. See, the radial nodes will be n minus L minus 1, okay? And the angular nodes will be how many? L, okay? So that the total number of nodes for the wave function is n
Yes.
minus 1, n minus 1, okay? Now, 6G. So what is G in terms of L? S, P, D, F, G. So if G is 5, what is the number of radial nodes that we have? Do we have? G is 5. This is, sorry, S is 0. This is 1, 2, 3, 4. So what should be the radial node? 1. And the angular node 4. I think Madhu, we have a mistake in the problem, right?
Yes, sir. It should be 1, sir. But one no option is there, sir. Yes, sir.
Yeah, 1 and 4, right, Madhu?
Yes, sir. 1 and 4. 1 and 4 is correct. Yeah.
Is it there as the answer?
No. We have given 0 and
0 and 5. Yeah, 0 and 5 is wrong. Yeah, 0 and 5 is wrong. Because S is 0, L equal to 0.
Hmm.
This is L equal to 1. And therefore, this is L equal to 4. G is L equal to SPDG. So you are right. Thank you. So this we will correct. We will correct the answer today itself. Can you upload that correction today? Everybody will know the answer.
Yes.
Okay. Everybody will know the answer. You do one thing. You put 1 and 4, you put 2 and 4, and you put 3 and 2, something like that. But Sandeep has already corrected the answer. Okay. That's correct.
Okay, sir. Okay.
Thank you. Yeah, that was right. That's a mistake. I'll take care. Thank you.
Okay, sir. Thank you, sir.
Thank you. Yeah, I think this is important. You guys have to go through it very carefully, and then you will know what mistakes we make. Okay? No matter how many years we teach, we still make mistakes. Okay. Thanks, Balaji. We can